Please watch this video before you make even one more part drawing using GD&T. Specifically, if you're going to call out datum features or make datum references in feature control frames. If you are like 90% of the mechanical engineers and designers that I know, if you make drawings, this is going to be the best thing you see all day. You know, like so many things, there's a million ways to get these callouts wrong, and a much narrower set of ways to get them right. Okay, so this is my video on bogus datum reference frames. You might call this part an adapter plate of some kind. Very common. Here's the CAD. We can take a look at something like this and probably take some really good guesses about its function. I always think that when you see these patterns of screw holes, that's the biggest clue right there. Because if there's screw holes, that means there's screws that attach another part to the surface that the screw holes are normal to. This part appears to have two patterns of screw holes. You have the threaded holes on top, and you have the counterbore screw clearance holes that go through the part. The threaded holes are blind, okay? They don't go through the part. So whatever attaches through them comes in from this side. So it's an extremely good guess that something attaches to this side of the part. Next, we can see from the direction of the counterbores that screws must go through in this direction and attach this part to another part in a higher assembly level. So this is a very common thing, I think, for a part, that it attaches to something and something else attaches to it. So it has at least these two interfaces. And I can see two primary datum features, the bottom surface and the top surface. Let's have a closer look at the interface on the bottom here, where we have some other features that really sure seem to be like locating features for this interface. I would say that cylindrical pocket in the middle sure looks like a locating feature, like a secondary datum feature, and the notch looks like another locating feature to control the rotation, a tertiary datum feature. On the other hand, it doesn't seem like we have any other like really special locating features on the top. So let's just go have a look at this assembly where this part's being used. Okay, so sure enough, we have this funny little green tube part that attaches up top. Then the whole thing screws down onto this blue part, which we'll say is like a detail area of a larger part. All right, and so I'll just collapse it so you can see how it all looks together. Let's have a look at this drawing, which is GD&T 00531, and reflects an approach to this that I see designers taking pretty often. Real quick, let's just get through the callouts that define the bottom interface, but what I really want to talk about is what's happening on top. So let's have a look, okay? I put a flatness callout on the bottom surface, and I'm calling it the datum A feature. Then here in this detail view, I have my datum B and datum C features called out and related. So then when we come back up to this view, I can use that datum reference frame A primary, B secondary, C tertiary to locate the perimeter of the part and my counterbore through holes. All right, so I have this 25 millimeters plus or minus a half a millimeter on the thickness, and then I go to the top surface to talk about my threaded holes. So let's talk about the position call out for this pattern of M6 threaded holes, especially the datum references, because this is what I see a lot of engineers doing, and it's not quite right. Listen, I know what's going on here. They're thinking about the coordinate system created by the ABC datum reference frame, and they're seeing that this top surface is parallel to the bottom surface, and they think, okay, I'll just use that same ABC datum reference. It's close, but it's not quite right, and I'll show you why. That would have been the right call out if the assembly was like this, a little weird. What's happening here is that the gray part attaches to the blue part, but then some other elements of the blue part kind of like bridge over, and then the green part sits on top of the bridge, and some longer screws must go through all the way through the blue bridge and into the gray part. This way, even if the top surface of the gray part was slanted like this, within the size tolerance, the threaded holes would still be controlled as normal to the bottom surface. But that would be a pretty uncommon way to use the threaded holes on our gray part, wouldn't it? We want this far more common usage here, right? And if the top surface is wedged relative to datum A like this, we want those threaded holes to be normal to the top surface. And to get to that, the top surface needs to be a primary datum feature. Okay, so let's go have a look at another drawing of this part. This one is GD&T 00532. Everything should be pretty much the same with the datum A and the datum B and C features. Only now when we get to the top, you'll see that I'm calling out that surface now as our datum D feature. And now my great GD&T peeve, let's look at the datum reference now for the M6 threaded holes. D primary now, B secondary at MMB, C tertiary at MMB. This is what I call a bogus datum reference frame. It doesn't exist and it can't be used. Let's think about this. We're saying that our gray part locates onto the blue host part with these locating features. But then we're also saying that the green part locates to the gray part on the top surface as primary, and then picks up the locating features underneath as secondary and tertiary? What does that even look like? I guess it would be like if the green part screwed down on top, but then wrapped all the way around to pick up the features on the bottom somehow. How could this even be assembled? How could we attach this green part to the gray part on top and then also attach the gray part to the blue part on the bottom with the green part in the way? You can't, because it's bogus. There is no datum reference frame, D primary, B secondary, C tertiary. Let's look a little bit more closely at the callout and see if you can follow along with this next point too. See how datums B and C are called out at maximum material boundary? Well, what is the maximum material boundary in this context? Because datum features B and C are called out referencing datum A as primary, not datum D. So if our top surface, the datum D feature, is wedged relative to datum A, what does that do to our wraparound green part? The datum B and datum C features, defined in orientation to datum A, would not fit in there. Okay, so I've showed you the bad examples, but now let me show you the way I think you should do this. And this is drawing GD&T 00530. You'll see that a lot of it's the same right up to this 25 millimeter dimension. There are some improvements here. I went for a basic dimension. I added a positional, orientation, even flatness control to the datum D feature. We're a little off topic here, but this is a more sophisticated way to control this surface than the plus or minus tolerance. Now when we get to the threaded hole callout, you'll see that there are actually two positional requirements. This top frame, somewhat familiar, controls the position relatively loosely within that datum reference frame, A primary, B secondary, C tertiary. Then the lower frame, a secondary requirement, controls this pattern of features to a tighter tolerance, controlling the features to each other and in their orientation to datum D. This 0.38 number is going to be the tolerance we calculate to get the virtual condition we need to guarantee fit with the green part. Do you see how this more correctly describes the intent and requirements of these features? The bottom frame says that the pattern of threaded holes has to work independently as an interface. And then the top frame locates them to the other features of the part. Okay, so ready or not, let's look at another example of a bogus datum reference frame. This one is drawing GD&T 00534. It's a housing, and it's a little bit of a shout out to our inch people out there. Real quick, let's start off looking at these general notes. Note 1 is a little disclaimer about the drawing being incomplete. And my note 5 here applies a profile tolerance to all the unspecified features. This is pretty common on drawings these days. Okay, so our large flat mounting surface here, we're going to call the datum A feature. And then this pattern of two cylindrical bosses, we're going to call the datum B feature. The screw clearance holes that hold this thing down are going to reference datum A primary and datum B secondary at MMB. All right, so far so good. So let's see what the problem is. And for that, we'll come over to the side of the part. Now, I think this would be a really common way to see a lot of engineers and designers approach these 125 through holes. And to see the way they get there, largely by just following the way that the part is dimensioned. Someone might say, okay, I have this flat surface here. It's normal to my 125 holes. So this might be my primary datum. And so we'll come in and call that datum C and say that it's a 3 degree of freedom primary datum feature. And next I have my datum A feature, which is perpendicular to my datum C feature. And, maybe that could be a nice 2 degree of freedom secondary datum. And what's left? Well, I guess I still need to control the position and one more degree of freedom. And from this vantage here, it sure looks like that datum B feature of size will do it as a tertiary datum. So I end up with this datum reference frame, C primary, A secondary, B tertiary at MMB. Right? Wrong. There is no datum reference frame CAB. It's bogus. What do we think is the part that attaches to these holes? I can believe that it would use the datum C feature as a primary datum. But what I can't believe is that whatever attaches here is going to pick up the entire datum A feature and locate off it. And I definitely don't believe it's going to locate off of the datum B features. And a call out like this could become needlessly difficult in inspection. What I like to do in a situation like this is to imagine an inspection fixture. And I make them purple so that you can recognize them and you can think about them as being highly geometrically accurate. Perfect for our purposes. So this fixture would have datum simulators for C, A, and B at MMB. And then there are 2 holes in the fixture down here for our hole locators. So we would set our housing part down on this datum C simulator and then slide it toward the datum A simulator until it makes 2 points of contact, right? Does this seem plausible so far? Well, what happens if the datum C surface is not very square to the datum A surface? We stay in full contact down here to the datum C simulator, but then on the datum A simulator, you end up with all your contact happening right there at the top. And then down here, there's really no chance we're going to get the hole locators through. It also looks like our datum B features are not engaging in their datum simulators very well. This top one up here is interfering, and this bottom one down here isn't even engaging. Okay, and speaking of those datum B features, let's see what this looks like if the datum C feature is out of perpendicularity, but in a different direction. Seems like here maybe we could get our hole locators to go through. But in reality, we wouldn't even make it that far because we'll never get these datum B features to engage in the datum simulators. So I told you that CAB datum reference frame is bogus, but I'll go a step further. The datum A feature is a primary datum feature, but it is a poor secondary datum feature for the same reason it's a good primary datum feature. It's so big. And the datum B feature pattern is a good secondary datum feature, maybe even pushing the limits as a 3 degree of freedom secondary datum feature, but it is a poor tertiary datum feature because it's so complex. You can get away with a 3 degree of freedom secondary datum feature in this circumstance, but for tertiary, it's just too much. So maybe one thing to say is, don't try to force these features to become something that they're not. These datum references aren't alphabet soup. Your datum reference frames should generally be very directly associated to the various interfaces between your part and the other parts that attach. The idea that, for example, a tertiary datum feature from one interface is going to be doing double duty as a secondary datum feature for another interface, you just don't usually see that in designs. So let's go have a look at a more correct version of this housing drawing. This one's going to be GD&T Guy 00533. Until we start looking at the side of this part, there's going to be a lot that's the same here as on the drawing 534. So let's start with this profile and perpendicularity callout on the datum C feature. This is a little bit better control. It's good. And now for the 125 holes, I'm back to my old bag of tricks. We have 2 position requirements in 2 different datum reference frames. Datum reference frame A primary, B secondary at MMB could be simulated by a special fixture like this. We have our nice flat top surface datum A simulator. And then I put these fun inserts in here that would be our datum B at MMB simulators. My thought here is that the inspector could indicate in this fixture and then locate the 000 of that coordinate system right at the top of this center hole. And then I can set my part down on the fixture, and I can use special hole locator pins to verify the position of the screw holes in that datum A primary, B secondary datum reference frame. And this all makes a lot of sense because those holes are part of that same interface. And back to the drawing real quick. On my general note 5, I have a profile tolerance for all the unspecified features. And because now our inspector knows where the 000 of this datum reference frame is, they can go in and touch off on all the unspecified features and see if they meet the requirement. Can we find the surfaces of this slot in the XYZ space of that datum reference frame? Sure, it's right in the CAD model. Does it matter that the direction of cut of the slot is not normal to datum A? Not a bit. Same thing with the 125 holes. Yes, they belong to a different interface. No, they are not normal to datum A. But for these on the drawing, I do have basic dimensions locating them back to datum A and datum B. And in the hole callout, I give them a position in that datum reference frame. And I just want to make a note before we move on that these holes have a maximum material condition of 124. And then if we were to subtract 20 thousandths, that would be 104 as the virtual condition, 104. And now if we go back to our inspection fixture, since we're having fun, what if we add a special block in here that's going to help us locate those holes in that datum reference frame A primary, B secondary? See how these pins are the 104 thousandths virtual condition? And that in here, well, there's quite a bit of clearance around those 125 nominal size holes. And that just shows we have a looser position tolerance in this callout. That's a good thing because these holes are probably drilled in another machining setup separate from all the other features that are made in this datum reference frame. It is good to have some control though, at least just to keep them located on, for instance, this slot here. Check this out too. This is what happens if we have a little bit of orientation deviation on that datum C surface. It doesn't really have much of an effect on this inspection. Great. So how about this lower frame position tolerance on these 125 holes? This one is 4 thousandths diameter at MMC, referencing datum C primary. And just a quick note, we still have the 124 thousandths MMC, and then we subtract 4 thousandths this time, so we have 120 thousandths virtual condition, 120. Okay, for this inspection, gone is the fixture, and it's been replaced by this cute little gauge. It has two cylindrical bosses. They're exactly 120 thousandths in diameter, perfectly spaced, perfectly perpendicular to our datum C simulator, which is this flat surface. And this one just has to fit into these holes until the datum C feature makes solid contact against the datum C simulator. Well, what happens when there's some orientation deviation on the datum C surface? The gauge goes right along with it, and you find out if you still fit. Okay, now that I bet you're starting to understand me, let's power through a couple more examples. This next one is GD&T Guy 00537, which is a stainless steel flange. It has a 1.998 diameter locating feature, an O-ring gland, and a bolt hole pattern. I'm flagging this one as suspect because I have several callouts that use a datum A primary, datum B secondary, and MMB datum reference frame. But then strangely, I also have this callout for the 1.920 through hole, which has a very tight position tolerance, applying at RFS, no circle M, and then it references datum B as primary, RMB. This is a little sarcastic, but I'm wondering if there are two uses for this part. One where it sits on another part, locates on a 2-inch internal feature, and then gets bolted down. And then another use where there's a collet that comes in and grabs onto this tiny little lip. You know, when a cylindrical feature is called out as a primary datum, that's a 4 degree of freedom constraint. This feature is just not long enough to establish that. It would be extremely difficult, I think, to find the natural orientation of this feature with a collet, without just loading it up against the datum A feature. So let's say I find the person who made this drawing and ask them what's going on, and they tell me that their main concern is that the lip would become vanishingly thin. And so some of the alphabet soup and the messing around with material boundary modifiers is meant to tighten up the tolerance in some way. But that's not what the datums and the modifiers are for. You should not think of these as levers to tighten or loosen the tolerance. What they say is, these are the features on this part that locate onto other parts in an assembly. And the order of the letters and the modifiers, that just tells us how they do that location. So here's what I would tell my friend who's worried about that wall thickness. And this is GD&T 00536. We'll keep the same datum reference frame as all the other datum callouts, keeping datum B at MMB. And look, this datum B feature is very tightly controlled. There's only a 4,000 size limit, so we're not giving up a whole lot by keeping it at MMB. And then if you're thinking about preserving wall thickness, you got to think LMC, circle L. We got that here in this callout for the 1.920 feature. LMC reverses the incentives from MMC. In MMC, the bigger the hole, the more positional deviation you can accept. So if we're at MMC, this hole could get bigger and it could keep walking off farther, which is exactly what our designer was hoping to avoid. With LMC, it's actually the smaller hole that gets more position tolerance. So if I'm the machinist, if I aim for and I get 1.920, I actually have 10 thousandths of position tolerance here. And if I go smaller, I get more position tolerance in a one-to-one sort of way, so that the wall at its thinnest point doesn't get any thinner. Okay, great. I have one more example, and let's just change it up a little by starting looking at an assembly. And I guess this is kind of just like a partial assembly here. We're going to be looking at this gray bracket that appears twice here. Okay, and then on the top and the bottom, we have these like extrusions. Maybe this is just like some generic CAD so we can see how these other parts are supposed to work together. The bracket has a tongue or whatever you want to call it that locates into this groove, and then we have these bolts and T-nuts. And then there's this long C channel, that's this green part, that attaches at the ends with two more screws into the gray bracket. Based on what I've seen, I wouldn't be surprised at all if someone put this drawing in front of me for review. And this is GD&T 00539. In fact, this is probably the way I would have done the drawing in the past too, but no more, okay? Let's take a quick look at the datum reference in this general note 5 here, okay? A primary, B secondary, C tertiary at MMB. Then I have a similar datum reference for the 7mm through holes. So let's go to the callouts for those datum features and see what that would mean. The datum A feature is this 2x coplanar feature, and I totally agree with this, no problem. And then the datum B feature is this perpendicular surface. Okay. And then the datum C feature is this close tolerance tongue thing. Now I have no problem believing this is a locating feature and should be a datum feature. But it's so long and close fitting that it's likely to be a poor tertiary datum feature. It's likely to over-constrain the part as a tertiary datum feature. And I am not on board with the datum B surface as a secondary datum feature. It should definitely be a primary datum feature for these M8 threaded holes. And I can hear the argument now. Since the tongue feature is a feature of size, it should probably be the tertiary datum, where the datum B feature, the perpendicular surface, is not a feature of size. It should probably be the secondary datum feature. Right? Wrong. I don't think datum B belongs in there at all for the callout for these 7mm holes or for the general notes tolerance. Does that datum B surface locate this bracket part in the assembly? I don't think so. When you think about how this bracket is going to be located in assembly, the tongue and groove is going to have way more influence, at least side to side here and in orientation. And the bracket is kind of meant to slide forward and back along the rail. If this C channel is twisted or not very straight, it's probably also compliant enough that we can force it into position when we go to bolt it up against the brackets. So these brackets are located into the blue rails before this C channel even comes into play. You get me? And now let's go back to the drawing to see those callouts for the M8 threaded holes. Okay, yeah, here we go again with the alphabet soup. We're referencing datum A, which is a primary datum in another interface, as our secondary datum here, and we're carrying over datum C as tertiary. But we just saw in the assembly, the C channel doesn't locate on the datum A or the datum C feature. It doesn't even come near them. So that's another bogus datum reference frame. B primary, A secondary, C tertiary. Doesn't exist. All right, so I've been doing this to you this whole video, but if those callouts are wrong, then which callouts are right? Well, here's another version of this bracket drawing. This one's called GD&T 00538. And this one has a few changes that should make a big difference. Well, first of all, we have some callouts that reference datum A primary and datum B secondary at MMB. And in the views, we can see that datum A is still that 2x coplanar feature, but now B is the close tolerance tongue feature. Great, because this is how the bracket actually locates into the rail. It's actually free to slide left and right. And now we're still calling the perpendicular feature a datum feature, and I've added a little bit extra control. So now we're controlling the position with a profile callout, and we have a couple levels of perpendicularity control. All right, and now onto the callout for these M8 holes. I'm worried I'm starting to turn into a one-trick pony for you, but maybe the repetition is good. We have a small pile of positional callouts here. The one thing that's a little bit different in this one is we have the composite positional tolerance I thought I'd throw in there for you. These are the top two frames of the 1.2 and the 0.8 position tolerance. The 0.8 will control the orientation of the pattern a little more closely to datum A. I think that makes sense here, so we can make sure that that long C channel is going to attach in there straight. And then the 0.5 position, referencing only datum C, is going to control those threaded holes as a pattern and control them in their orientation perpendicular to datum C. I hope you can see that this is a more accurate, more correct callout for the function of this part, and that it would be less burdened in inspection than the callouts with the bogus datum reference frames. Okay, well, that's what I got for this topic, at least for now. And I hope this helps you understand these datum reference frames better, the hardest thing in GD&T. So happy drafting and steer clear of those bogus datum reference frames.